And so if Ilaria, did you start recording?
Yeah, I do.
So please, Tom, you can go ahead with your presentation. Thank you.
Yeah, thank you, Carlos, for the introduction. Yeah, it's really glad that today I have the opportunity to introduce TLSeq to everyone here. You see the title, you can tell is the TLSeq, but basically is the purpose is generate long-range sequencing information without a long-read sequencer. So here is let's see the next slide. I think everybody here is very familiar with NGS sequencing. Currently, the short-read sequencer is the most popular one. It's higher throughput, higher accuracy. However, the limitation with short-read. And for this particular application, we look at how to facing haplotype, because with a shorter read length, it's limited capability to face the SNP pretty far away. On the other hand, long read for sure. So this example is PacBio. They have two different modes, a high accuracy mode and low accuracy mode. Yeah, they definitely has much longer read length, increase the capability to face the SNP or variants pretty far away. So currently for PacBio hi-fi chemistry, it's the length anywhere from 10K to 15K. For the low accuracy mode, it's 15K to 50K. It's pretty good. The limitation is the cost and sometimes it's accuracy. So what we've been doing here is TLSeq, it's a link rate. What that means is we're able to use a short-read sequencer. In this particular case, we use the Illumina sequencer because we still generate the short read. However, for those long fragments, before they break down to short read, we put a unique barcode over there. By doing that, we're able to track in those short read coming from which long fragment. So we have much long range sequencing information, even though we are not truly the full length long read. So there are gaps in between. However, based on barcode information, we can indeed tracking where they're coming from. By doing that, we can generate much longer range information. Here we can go up to 200 KB. So by this way, we can actually face the different long range variants efficiently using short read. Again, go to the concept is how link read work. Now, so instead on top is a standard shotgun sequencing, you just break down everything and then you try to assemble. So this become more challenge. However, for link read, I use this book series example. So instead you shred everything all together. You actually separate them by pages first. Then for each page, you shred them into smaller pie. Then later you assemble back. It will be really easy. For sequencing, the page for our particular case will be barcode. So we use a unique barcode to label each long molecular DNA, and for every subfragment breakdown from that long genomic DNA, they're going to share the same barcode. So that serves as a page function, and we'll simplify the assembly later. Again, the things what we're doing here is, it's just some modification on the library prep. We still use a short read sequencer to generate the long read information. As I mentioned, for TLSeq, it's a library kit. Another advantage is for our prep, we need a very low amount of input material. It's only from 0.1 nanogram to 5 nanogram. And with the accuracy from the short read sequencer, with the high throughput at low cost, we can working efficiently to get a long read information. Compared to the long read sequencer, another bottleneck is that they need much higher input material compared to us. So how exactly the TLSeq worked? So TLSeq specifically, the advantage is it's purely a library prep kit without any special requirement, additional special requirement for the library prep. So everything happened here. You can see for each sample, you only need 1.2 ml PCR tubes. In the 0.2 ml PCR tubes, the key thing is the tail beads. Tail beads is a bead. On each bead, there is it's barcoded beads. Each bead, there's thousands of oligos to share the same barcode. So each bead has one unique barcode, but we have millions the different bead interaction. So in the PCR tube, you have tail beads, we have transposome, and then you have the sample DNA put in there. And the magic happened this way. The first reaction is a barcoding reaction, which means it's the transposome attack the genomic DNA and pull it down to the bead surface. Here, what I show is that this is a bead, one bead. On this one bead, you can see the yellow bar is the barcode oligo. And so in the reaction, genomic DNA being attacked by the transposome and attached to the beads. Once the long genomic DNA fragment attached to one bead, they're going to stay there and be labeled multiple times by the barcode on the same bead. So, which means all the fragments coming from this long genomic DNA will share the same barcode. The next step, we introduce another transposome, this red one. The purpose here is that we need to introduce another priming site for the PCR amplification later stage. And after this reaction happens, yeah, another thing I did not mention is when transposome attacks genomic DNA, it forms a very stable strand transfer complex. So this thing is so stable until you use flash condition to denature it. Before that, yeah, it's everything stay there. Same thing when you do the second tagging, it still stay there until we said, okay, we want to stop a reaction. During this stop reaction time, now this strand transfer complex is dissolved, so release the fragment DNA. And this still on the beads. The next step will be we use a primer amplify from the beads direction and another end from the red transposome. So this will be the final sequencing library because we can't design for the Illumina sequencer. So actually during the amplification, we add a P7, P5 primer. So now we generate a Illumina library, which can be sequencing on the Illumina sequencer. The whole process is pretty streamlined. It takes just over 3 hours, starting from genomic DNA and all the way including the library quantification, and then it's ready for sequencing. It's again, as mentioned, depend the genome size. Our input requirement anywhere from 0.1 nanogram to 5 nanogram. So for bacteria, yeah, it's 0.1 to 0.5 nanogram is enough. And for human, we use close to 5 nanogram. Yeah, this is so after sequencing, again, this is try to estimate what's the link read length. Link read length, remember, what's the sequencer generator still the short read. However, based on barcode information, we can, based on the reference for this purpose, we need a reference, we back calculate to estimate what's the linker molecule length. So here is the distribution of linker, the molecule length. And you can see that the peak around 50 kb, and you have a significant amount of DNA to go 100 kb, so some even around 200 kb. So this is the power of the linked read sequencing, tail-seq sequencing. It's because, yeah, even though it is short read, we actually can provide as long as 200 kb, the long-range sequencing information. After sequencing run, because this is kind of unique procedure, so we do need some special analysis. For sure, is all the data it should go to the tail read pipeline. We consider this as a QC pipeline. The purpose here is we use tail read tools to do some barcode error correction, error filtering, and then make the output FASTQ file. Afterwards, there's a multiple direction to go for the people. If you want to do de novo sequencing, you can use our own assembler called the TailLink to the de novo sequencing. And if you want to do the phasing, you can use the TailSort pipeline to do the phasing analysis. Our software is freely available. if you need, you can go to our website to download it on your server to run it locally. Or is we already working with Illumina, we post this app for the tail-link assembler on the base space. We currently also working with Illumina. We're going to post get this facing app on the base space. Based on the schedule, it should be in early April. This app will also be freely, and this is not freely actually. Since you use the Illumina base space, they will charge your computer time. Yeah, by the starting from early April, this should be also on base space. Another alternative way is because it's link read technology have been existing for a while, especially 10x early had their own analysis, and also there's some third-party tools is available. If some third-party tools can directly use the tail-seq output data, but some it's all designed for 10x type link read. So for that purpose, we do have a pipeline. We can convert tail-seq data format into 10x data format. Then you can use the 10x to do it. The next, I'm going to break down some applications, give a little bit example for each application, and to just show the capability of the tail-seq. The first one is for the microbial sequencing. This is work has been done by Illumina team. What they use is they use commercially available genomic DNA, use tail-seq to develop the to prepare the library. Then on the Illumina sequencer is MiSeq or MiniSeq, and generate the data, analyze with the tail-link assembler on the base space. You can see again, I have not mentioned this yet. For long-read sequencing or long-range sequencing, one of the important criteria is you want to start with high molecular DNA. And in principle, the better quality high molecular DNA, you will get the better either for long read or link read better result at the end. For this particular case, the Illumina team they just use commercially purchased the DNA. Its average performance you see it's not too bad and not too good, because the issue is you do see. Just a second, I cannot find my cursor. There's quite a lot of DNA. It's under 10 kb. However, you do see it's also pretty good portion. It's above 60 kb. So for us, based on the data what we're having, we think for microbial DNA, if you can get average DNA is 20 kb or above, this should be pretty reasonable input. And however, for the large genome, for example, for human, if you want to get good performance, we really recommend it. You want to have a high molecular DNA as large as 40 kb by average to get a better performance for the large genome. It's again for the bacteria smaller genome. Of course, it's always the larger the DNA, the better. However, if you have an average around 20 kb, it's good enough. So I'm going to show you the data to see the performance. Here they have 8 different DNA input. We do see that in our reactions for GC-rich sample, the library yields will be a little bit lower. So it's the AT-rich and the GC-neutral more or less yield similar. The GC-rich sample, the library yield is a little bit lower. So here's the performance. It's again, as I mentioned, in this particular study, they use 8 different microbial with different GC content. On the left is AT-rich, on the right is GC-rich, and some of the you can see some of the bacteria they have both chromosome and also plasmid. There's 2. This another one has 5 plasmid. What happened here is again for this prep, for each one use around 0.5 nanogram genomic DNA for the tail-seq library prep. After tail-seq library prep, after sequencing, as I mentioned, the first thing our pipeline we call the tail read analysis. they give you some QC output. For this thing, for the tail read to work more efficiently, ideally, you want to have the reference. The practically is, of course, especially you do de novo sequencing, quite often there's no reference. Yeah, if no reference, yeah, you still want to run the tail read analysis. They're going to do some barcode error correction and filtering. Probably that's it, they give some barcode count. If you have the reference, this will be the purpose for us to optimize chemistry, evaluate the library performance. With the reference, then immediately we can do some calculation. For example, one of the important calculation, we estimate what's your genomic DNA, what's the link read molecule length. So here is the mean super long fragment size reflect on the link read molecule length. You can see it's anywhere from average 25 kb to the smallest one is 15 kb, the longest one 27. So this is more or less similar to what you see in the previous GEV. This particular sample, relatively speaking, the average is smaller, but yeah, this is good enough for bacterial sequencing. The next one is for de novo assembly, use the tail link. You can see that most of them assemble into the only one scaffold. You see the number contig greater than 10 kb, it's 1. This one has 2, remember, because for this particular genome, there's 1 chromosome, 1 plasmid. So indeed, is the whole genome has been assembled well. This one actually, yeah, it's one piece is broken, so there's a 2 long contig. The overall, you can see is that, yeah, it's a majority bacteria can be assembled to almost a full-length scaffold with very minimal error. As I mentioned, that there's 3 of them has plasmid. Yeah, two of them not only chromosome assembled very well, and also the plasmid assembled pretty good. The last one has a 5. Has 5 plasmid. It's pretty challenging. So some of them being assembled, some not. So overall, it's a if you have good DNA, it's quite often you're able to both assemble the chromosome and plasmid into the right place. Previous, I mentioned that in the video microbial sequencing, we also start to look into the for the metagenomic application. Currently, again, what I talk about here, metagenomic application is a whole genome sequencing based application. Our current approach is after whole genome sequencing, we do the de novo assembly. So current limitation for our approach is the de novo assembler, which is our tail link. Our tail link is working really well for the smaller genome. When I say smaller genome, it's usually referred to as anywhere is probably under 100 megabase is better. We do believe it's a tail link assembler can work up to 200 megabase for the genome side. So this is kind of our limitation for this assembler, because for our current approach is after whole genome sequencing, we need to use this assembler to make a contig. Then we do the further analysis on the abundancy, on the composition, identification, use the contig to do the analysis. So our current assembler has been limited in terms of performance, is under 200 megabase. So which means for the metagenomic sample, use our current approach, we can only working for relatively low complexity samples. We kind of thinking it's probably the sample contained no more than 40 or 50 organism. If for complex sample, quite often the fecal sample probably just too complex at this moment for us because our assembler cannot work. So here the example what we're showing is did a Mach 20 sample with different abundancy. It's 1,000-fold different. Use the assembly-based method. Yeah, we can detect the first 3 order. The last one, since the abundance is so low. The abundance is so low, so it's hard for assembler to making good assembly. That's why it did not detect very well. However, we go back to look at data on the read level. So indeed, we indeed find that the read represent those organism and with it kind of expected the proportion to ratio in those samples. So this tells us the advantage and limitation for this method. For this method, since we do the contig assembly, we do get a much better information on the gene potentially for the pathways, the metabolic pathways have a really good application. But also because it's based on the assembly, so for the low abundance organism species, you're probably going to have a hard time to assemble them properly. It may not be able to detect efficiently or effectively. So currently, we also internally working on another approach. It's to use a read-based method to simply more purposes for the identification or the composition analysis. This is working in progress. We're also looking for the collaborator in this area. We do believe it's for tail-seq link read, there's a really good potential in this area. Again, there's some more work need to be done on the analysis, which we're working on, and also hope that the field can help us working together on this area. I'm going to previously talk about the microbial application, and now give some example for the other genome. This particular example is from one of our customer at the University of Illinois. They're focused on the sequencing some insect genome as part of Earth Biogenome project. So their approach is once they got the DNA from the samples, they use the tail-seq, they make tail-seq library, do the tail-seq sequencing. So because again, this is de novo sequencing, right? So they have no idea what's the genome complexity, what genome size. So they use the tail-seq data to estimate the genome size. Yeah, but based on that, they can decide what they need to do for the overall assembly approach. So in their approach, they use the PacBio data to make the initial assembly, and they're also making the high-C data to further scaffolding. So in this particular strategy, yeah, they use the PacBio data to make an initial assembly based on the information from tail-seq in terms of genome size. You can decide how much sequencing depth you need to do on PacBio. After that, again, they're going back, look at the tail-seq data to scaffolding, further scaffold the PacBio data. And now they also check is after this process, they also see is if it's add on the high-C data to see if it can further improve the scaffold. So this is the approach they've been evaluating because their purpose is they want to set up pipeline for hundreds of thousands of samples. So here the data, what I'm showing you will be from this study. And after scaffolding at the final assembly, they can further use the tail-seq data to do the gap filling and some other biological analysis. As I mentioned, they use the tail-seq data to do the initial genome size estimation. What you can see here is the blue bar. There's 10 insects. Blue bar is actually the sequencing determine the genome size, and the orange bar and the gray bar is a different method to use the tail-seq data to evaluate the genome size. And the way how they use tail-seq data evaluate genome size simply is consider tail-seq data a standard shotgun read that they can estimate the genome size. Ideally, you're expecting both the blue bar and all the other color bars should be similar. So more or less, for most samples look similar. However, you do see the two samples appear that the actual genome size is much smaller than estimate the genome size. The reason it turned out is very interesting. What they find out for this particular case, they have a lot of read. It's coming from endosymbionts of pathogens in the insect gut. So that's why they have a lot of other foreign DNA being sequenced that affect the way to estimate genome size. So based on this information, yeah, they realize ideally for those insects, if possible, yeah, you don't want to extract DNA from the gut. but sometimes it's hard because so small, they have to use the whole insect. However, if possible, yeah, try to avoid you use the gut tissue. Yeah, that will be carry over some contaminants, then making the genome sequencing is more difficult. Here's the assembly result. I pick 3 samples. As I mentioned, their approach is they use a PacBio data for the initial assembly. So here show the line scaffold and the N50 scaffold. Then they use tail-seq data to do the scaffolding. You can see we can input the longest one or to input the N50. And they also try to see on top of that, add high-C or mini-C data to see can further input the scaffold or not. So for the first case, it's a high-C data have some improvement, but not that significant. The second sample, yeah, the high-C data can increase the longest scaffold, find nicely, but overall for N50 did not increase that much. The tail-seq for sure is significantly improved both the longest and the N50. For the last one is so since the material is limited, so they cannot even make the high-C sample. So from the tail-seq data, you can see it's again significantly improved PacBio the assembly result, both on the longest scaffold and N50 scaffold. So here what I show is use tail-seq is another usage to scaffolding the long-read assembly result on the insect samples. These slides show that we can also actually use the tail-seq data working with ONT, oxynanopod sequencing data to scaffold. So this particular example on the left is ONT alone, on the right is ONT and tail-seq. Again, same stories. You can see tail-seq can significantly improve the longest scaffold and also the N50 scaffold length. Now I'm going to switch the gear a little bit, talk about for the human application. One of the first example is for the whole genome, the facing application. What you can see here is we sequence 2 reference human samples, 12A78 and 24385, the genome bottle samples. You can see the for our rate, we have very good over 97% mapping rate. And then this is another way to look at linked read molecular length. It's about over 90% rate greater than 20 kb, and 20-30% linked rate is over 100 kb. So for the whole genome sequencing, you look at the variant SNP and the indels. Yeah, you can get for the SNP, both record rate and precision rate is around 99%, similar as standard shotgun data. And for the indel, it is about 90%. It's more or less comparable with standard shotgun performance. For facing, here's the purpose we do for facing. You can see that we can get the longest face block close to 60 megabase, and for N50 face block, it's over 10 megabase. It is really good performance with very low error. That's a whole genome sequencing. We can zoom in to look into one particular region people interested in, which is MHC region, contain a lot of HLA genes. We can face this about 4 megabase region. We can face into one complete haplotype. But basically, this is 2 haplotypes because one from maternal, another from paternally. So this is a really nice demonstration the capability use the tail-seq for facing application. This particular example to show is that we can use the face data to identify the structural variation. This particular example is in the 12A78 in this particular location. Early publication showed that here probably is homozygous 19 kb deletion. Another publication showed here is 114 kb heterozygous deletion. We look at our data, yeah, that we realize actually is in this particular location, it is within 114 kb heterozygous deletion, there is a homozygous 19 kb deletion. So this demonstrated that the power of tail-seq can detect this long range, the large deletions in the genome. For the SV analysis, one of the challenges is how to use software automatically to able to making the SV calls. At the moment, there's no perfect solution yet, and on the market, there's several different tools. For early days, 10x, they have their own long range. So for long range analysis, relatively speaking, it's take a pretty long analysis time. So here is on the right, talk about how long it takes to finish phasing and as we call using long range. And for as I mentioned, if for tail-seq data, if we want to use a long range in the middle before it, there's one step you need to convert the tail-seq into 10x comparable format. We supply the tool over there. If we want to do this way, yeah, it's all the tools are available. At the same time, we recommended another workflow is for there is a different tools they can use tail-seq sequencing output directly. For this is we actually look into both short read SV caller and link read SV caller. So the first tool is link read SV caller, and then the next tool is short read SV caller. Current recommendation is it will be good actually run all 4 SV caller for the same data set, because we find is for any single one they have they only been they only been detect a part of the SVs. So that's overall for the SV calling in this field. For link read, there's still no perfect solution yet. We've been working with collaborators to trying to further improve the performance. Meanwhile, also work on the users working with us for further improve this performance. So currently, our recommendation is to use multiple tools to get a combined result, have better coverage. For large genome, for phasing, it's again, as I want to emphasize, it's very important. It's the quality of genomic DNA input. Here, the example what I'm showing here, you use phasing as a particular metric. You can see the y-axis is the phase block length. The x-axis is the molecular DNA length. That's kind of more or less related to genomic DNA input side. So you can see it's a kind of like a exponential relationship. At 20 kb average genomic DNA, you got N50 megabase, N50 block. It's about 0.5 megabase. It's if by your genomic DNA input around or sequencing linked molecular length around 40 kb, you actually get around 3 to 4 megabase and 50 phase block. So this like an exponential relationship. It is again emphasize the importance for use a very good high molecular DNA as the initial input. Not only you need a good high molecular DNA to into the reaction, during the reaction, because our library prep also have several steps. There's some manipulation. You have to be careful to try to reduce damage during the library prep, because indeed we find out that if you prepare too harsh and if you don't take care, even you have very good genomic DNA start with, you're still going to lose those long read information because they can be break during the library prep. Previously, I talked about the whole genome scale, and now if people are interested, we also have the solution to look at the targeted area. For targeted area, there's a different way to look into. If you're familiar with the probe capture method, this particular example is use exome sequencing. So we can just modify existing exome sequencing. So normally for the exome capture, you use make a whole genome sequencing library first, then use a probe to capture. For our approach, we simply replace the standard whole genome sequencing library prep with the tail-seq whole genome sequencing library, then use a short select chemistry to capture since our library is we change the adapter sequence, so we do need to use a new blocker. So after that, you can capture the library, then do the sequencing. After sequencing, we can look into here's the in terms of facing data. We can get 85% SNP phased and around 77% gene phased. It's another way to generate phased information from the probe captured targeted application. The next approach is so now if we have good way to enrich the particular long contiguous target, for example, if here use the BRCA, BRCA2 gene, if we can find a good way to really isolate this full gene genomic DNA from the target, and then we only need to sequence this particular region. So that's exactly this approach did. It's from our collaborator Sage Science. They developed HLS catch method. It's CRISPR-Cas9 based method. They starting with cell, design the guide RNA to cut the target. This particular example is BRCA1, BRCA2, each one around 200 kb target. They cut it from genome and then use electrophoresis to isolate this long piece of DNA. And the recovery is kind of low. It's anywhere from 5 nanogram to 20 nanogram. However, for us, it is plenty because for tail-seq, we only need 0.1 nanogram to do the library prep. So with these days, we can easily make the library, do the sequencing. We can face the 200 kb almost completely. And here is for the trio family. After facing, we can get a haplotype of 2 haplotypes for each patient, and then this is son. You can match up to their parent nicely, so you can know to validate the facing results is correct. Another way for the facing application is, if we have a good long-range PCR amplicon, you can use our protocol to face it efficiently. Here, I show you 2 examples. So one example is for the cancer-related mutation. These days, it's more and more information shows it's a lot of tumor actually have association with composite mutation, basically more than one mutation. That have big impact in terms of the cause of the tumor. So that also means it's important to identify the haplotype information among these mutations. This particular example, which is a PIK3CA gene, is know that 2 mutation is important for the oncogenesis. And to get these 2 mutation, the approach we're using here is actually starting with the cDNA. These are 2 design in terms of amplicon. One is a 3.5 kb amplicon. We also tried a shorter design, is 1.8 kb, still cover these 2 mutation. The yellow one is a SNP. So here what we're showing is start with the cDNA. If we amplify this 2 different lengths amplicon, later we're going to show the facing result. Before that, we have another target in the testing. This particular one is a sodium channel gene. It's found out for this particular gene, there's a multiple haplotype in the regulatory region associated with the risk. It's either increase or decrease risk for the sudden cardiac death. So this particular target, the full length is about 13 kb. Meanwhile, we're also testing the some smaller amplicon size to just show what's the limitation for the tail-seq. For this particularly, if you indeed want to get useful information for this one, you need to do the 13 kb, the full length amplicon. Here, the reason we do the smaller size simply for during this study, we evaluate some of the size effect for the tail-seq. Here's a summary in terms of the facing for these 2 different target, and we have different amplicon size, and we use a different approach. Is either is for each amplicon minimum is need 20 picogram input, and for the library preparation we need a total 80 picogram if we only have 1 amplicon. So we add some carrier DNA. If you have some other amplicon, you can mix different amplicon together to make sure minimize 80 picogram into making the tail-seq library, then do the sequencing. So here we have multiple technical replicates. For all of those different conditions, we can 100% identify all the heterozygous variants, and also we can 100% fix them correctly. Yeah, I think this is more or less is all I'm going to show today. In summary, hopefully I can show you guys tail-seq is a very simple library prep kit, and it can use the short-read sequencer and generate long-range information with this very low amount of DNA input. Yeah, that's all I have. Any questions?
So thank you, Tom. I think it was very clear and very well detailed. First of all, I'm not such an expert in NGS, so I think that people are much better than me about it. But I have a simple question. So can you use the tail-seq library on Illumina instruments only? Or because you in one of your first slides, you wrote Illumina or other second generation sequencers. So.
Yeah. It's a very good question. So far, our kit is in principle, yeah, we can use on any short-read sequencer. However, it depends the adapter is a library if it's the right adapter or not. So currently, our kit is designed for the Illumina sequencer. We do have a customer use this on MGI sequencer, and yeah, for MGI sequencer, so it's MGI have the converter kit can convert the Illumina library into MGM the library. So after that, yeah, there's some little bit change in terms of sequencing strategy. But yeah, we do have customer who also use our kit sequence on the MGI sequencer.
Okay, thank you. There is also a question from Adelaide in the chat box, so I'm gonna read it.
Sure.
Can I use tail-seq to sequence double-stranded cDNA, considering that I'm interested in sequencing viral RNA from clinical sample? Can I use catch plus tail-seq to enrich viral component?
Yeah, so for cDNA is in principle we can sequence. The challenge it is because our software so far is only being capable to do the like a differentiate the two haplotype. So for cDNA, the case is it's all depends if you actually interesting for look at different isoform. If it's more than two, we don't at this moment we don't have good solution how to fix them properly. Yeah, so that's the challenge.
Okay, thank you. So if I don't know whether there are other questions, so please write it down in the chat. So anyhow the webinar has been registered. So and we'll put it in our in Prodotti Gianni website and YouTube page. So if you want to give a look again, you can see it again. And so Prodotti Gianni, thanks Tom and Universal Sequencing for giving this exciting webinar. I think that tail-seq is a very powerful tool for people that wants to run NGS. And thank you all for attending the webinar. And feel free to contact anytime you need something. Thank you again. Have a nice weekend for Italy, and have a good day for Tom.
Thank you, Carlos. Thank you, everyone joining here.
Bye, everybody. Bye-bye.
Bye.